Hello, everyone. Welcome back to day two this week. We're going to be looking at some more samples or more examples of doing this hypothesis testing with the mean and looking at what type of tests we're supposed to use in certain situations and things like that. So, really, just a couple more examples of the hypothesis test, and hopefully, I'll address some of those more finer details as we go through the problem. All right. So let's take a look at this new problem here. We're testing for a mean. It says we have a random sample of heights of male high school basketball players included below. So we have a sample with some data here. And it says we know the population of all heights of basketball players is normally distributed. Okay, so that's a key piece of information there. So I noticed right away when I saw this problem that the sample was kind of small. I think there's only 11 pieces of data here, which for a sampling distribution is not quite large enough to normalize. But since the population of high school basketball players is already normally distributed, we didn't really need that big of a sample size. All right, so we're good there. Is there evidence at a 10% level of significance, I misspelled that, that the mean height of all basketball players is higher than 72 inches? So we're testing a claim. The claim is that the mean height of high school basketball players is higher than 72 inches, and we want to know if we have enough evidence from our data here to support that claim. All right, so we're going to start the hypothesis test. We're going to start with step one here, which is just to state the parameter of interest and verify our necessary assumptions, i.e. why the normal distribution applies. And we kind of already talked about that. We know that the normal distribution applies because the original population was normally distributed. We didn't have quite a big sample. We didn't have a sample that was greater than 30, but the original population was normal, so we're good there. The parameter of interest is mean, right? So we're testing something about a mean, and we're specifically looking at the mean height of high school basketball players. Okay, so it's always important to identify what parameter we're working with because it gives us a clue as to what tests we're going to use. All right, a proportion is different than a mean. A mean is different than a proportion, so they require different tests. All right, so step two, we're going to set up our null and our alternate hypothesis. Okay, so I'm going to set up a null hypothesis with a h with a little 0, and then I'm going to do an h1 or an ha, whatever you prefer here. And remember the rules for our hypothesis, our null hypothesis and our alternate hypothesis. Equality, whatever statement of equality we make, it has to go in the null hypothesis. It can never go in the alternate hypothesis. So our null hypothesis is almost always whatever the assumption about the population is, right? And it tells us that we're trying to test whether or not it's higher than 72. So I'm going to make the assumption that the population mean is 72 inches. So I'm going to say population mean is equal to 72. And our contradiction to that, or the alternate hypothesis, is that the mean is going to be greater than 72. All right, because it specifically tells us here that we want to know if it's higher than 72. Okay, so the assumption is that it is. We're testing that it's bigger than 72. All right, so let's keep going. We got our null and our alternate set up. Okay, step three here, we're going to carry out the tests, but which tests do we need to carry out? And I kind of put this table here to help us think about that. We've only learned about 3 hypothesis tests in this unit so far. There's the z-test, the t-test, and the one-prop z-test. So the z-test and the t-test are both used when we're making a test about the mean. Okay, so these test the mean. The one-prop z-test tests a proportion. Okay. The difference between the z-test and the t-test is whether or not we know about a key piece of information. Okay, we use the z-test if we know the population standard deviation. So if we know that little piece of information, we would use a z-test. But if we don't, if the population standard deviation is unknown, then we are going to use a t-test. Okay, so I need to go back to my problem and I need to see if they gave me any information about a population, specifically a population standard deviation, not a sample standard deviation. Okay, so I'm looking through this problem, and I'm just being very careful, making sure they didn't say anything about a population standard deviation. They did tell me about the population shape here, and I'm looking at the numbers. This is a population mean or a sample mean, and this is a sample standard deviation, but not a population standard deviation. And they didn't say anything about it here. So nowhere in that problem do I see a population standard deviation. So I'm going to assume that it's unknown, which means I'm going to be running a t-test. Okay, so this is kind of your differentiation here. For the one prop z-test, it doesn't matter if you know the population standard deviation or not. It's not required. You're always going to be using the one prop z-test for a proportion. All right. So we need to actually find the test stat or the standardized test statistic. This is what I call it for short, the test stat, and then the p-value. And I'm going to do this on my calculator. All right, calculator can calculate that stuff for us pretty quickly. If you want to see it done by hand, I suggest you watch some of the previous videos that I've done where I did all that work by hand for you, so you can see what the calculator is doing behind the curtain here. So we're going to go stat. We're going to go over to tests. And you'll notice the very first two tests here, you have your z-test and your t-test. Remember, we're doing the t-test. And we're going to use the data that we were given at the top of the page. Okay, so before you do the test, if you haven't done so already, make sure you enter the information about the basketball player heights from the sample into list 1. Okay, so I entered in the raw data. And you'll see a problem like that on MyOpenMath where they give you a table with some raw data. This is what you should do with that. You want to make sure that you put that into L1, and when you run your t-test, you're going to select the data option up here. Okay, then you're going to tell it what you assume the population the population height to be. Right? What's the mean population height? Well, we're assuming that it's 72. Then it wants to know, where did you put your data? Well, we put the raw data in L1, right? So list 1. Don't mess with the frequency. All right, then it wants to know, are you doing a left tail, right tail, or two-tail test? Remember, we're testing for the mean being greater than 72, so I'm going to select greater than U naught down here. Okay, and then that's it. All we have to do now is go to calculate, and we'll get our information that we need. So we got some numbers here, and I just want to walk through what these numbers mean again, okay? Because on the test or the quiz, I'm going to ask you to tell me what these numbers are in the context of the problem. All right, so this first one is our test stat. It's our test statistic, standardized test statistic, and what it tells us is how many standard deviations away from the expected value we are with our sample. So we took this sample, we got a mean. That mean that we got from our sample was 2.75 standard deviations away from what we expected to get, which was 72. That's what a test stat tells us. And you need to think back to the beginning of the semester, and we talked about standard deviations, and we had specifically talked about how many standard deviations away from something you need to be before we start to consider it to be unusual or rare. Okay, and that barrier was 2. So this is kind of looking like it might be unusual to get a test stat of 2.75. It might be unusual to be 2.75 standard deviations away from what we expected. Okay, so this next number is the p-value, this 0.01. And what the p-value tells us is, what is the probability of getting 2.75 standard deviations away from what we expected? Okay, so we collected this data, and the probability of collecting data and getting a sample mean that's 2.75 standard deviations away is only 1%. It's extremely unlikely. Okay, and remember, this is a probability under the assumption that this is true. So if we get a really low probability here, we stop believing that the mean height is 72. But how low does that probability have to be? Well, it has to be lower than our significance level. So if this probability drops too low, below a certain level, specifically the level we set with our test significance, that's when we stop believing this. Okay, we no longer believe that the mean is 72 inches if this is too low. All right, So let's actually record these numbers and finish off our test here. So our test stat was 2.76, I think if you rounded to the third decimal place, 2.76 standard deviations away. Okay. And our p-value was 0.01. All right, so we got both of those things. And the next thing that we need to do is we need to compare that p-value. Is the p-value low enough for us to stop believing that the population mean is 72 inches? So I take that 0.01, I compare it to the test significance level, which is 0.1, right, 10%, and 0.01 is certainly less than the 0.1. So what this is telling me is that I need to reject the null hypothesis. We have to reject it. The probability of getting this is too low for me to believe it anymore. All right, so now I'm going to write my conclusion in the context of the problem, right? I compared my p-value to the significance level right here, and I have decided to reject the null hypothesis. What does that mean in plain English? Let's write that out. All right, and there it is. I just typed it in. That way you don't have to watch me with my horrible handwriting with this tablet. It says there is sufficient evidence to support the claim that the mean height of all male basketball players is greater than 72 inches. Right? This was too low, so we rejected that the mean was 72 inches, which means we must assume that it is now greater than 72 inches. We don't know how much greater or exactly where it's at, but we know that it's greater than 72 inches at a 10% significance level. All right, so that finishes off our test. That's how we write the conclusion in context after we have compared our p-value and made a decision. All right, let's keep going here. Let's look at another example. So we've got rats in this one. And if you don't know this character over here, this is Brain. There was a cartoon a long time ago, back when I was a kid, called Pinky and the Brain. And it was about these two rats that lived in a laboratory, and their goal every single night, once the scientists all went home, was to break out of their cage and take over the world. It's a hilarious cartoon. You should check it out if you have never seen it before. All right, let's read this problem. The mass of a certain breed of rat at 40 days old is supposed to have a mean mass of 120 grams. Experimenters are testing a possible brain growth treatment that seems to have a positive impact on brain growth, but they are concerned about overall weight loss. A random sample of 41 rats undergoing the new treatment yields a sample mean of 118.8 grams with a sample standard deviation of 5.2 grams. Is there evidence at a 5% level of significance that the overall mean mass of the rats is less than 120 grams as a result of this treatment? So does the drug cause weight loss? Seems to be the question here. So I'm going to start with step one, state the parameter of interest and verify the necessary assumptions. Okay, so what we're interested in here is a mean again. We're interested in the mean of the mass of rats. So they're supposed to be at 120, but they're concerned that the drug is causing weight loss. So their concern is that the weight after the treatment would be less than 120. So we want to verify whether or not it causes weight loss. So we're interested in a mean for sure. And can we use the normal distribution here? So if you read it carefully, it doesn't say anything about the shape of the population of rats, but it does say that we took a random sample of 41. So we know the sampling distribution will normalize because the sample size is greater than 30. So we're good there. We know what we're interested in, and we know that we can use the normal distribution now. So we're going to go ahead and set up our null and our alternate hypothesis here. So H naught, alternate, there we go. So the assumption is that, or what the mean mass of a rat is supposed to be, right? The assumption is that it is 120 grams. So I'm going to go ahead and put my equality statement in the null hypothesis. And then the contradiction to that is that the mean is going to be less than 120 because remember their concern was that the rats are losing weight as a result of the drug. So we want to test against weight loss. Okay, so we want to specifically be less than 120. So this will be a left tail test. Okay. So then the question becomes, what test are we going to run? Is it going to be a z-test, a t-test, or a one-prop z-test? Remember, z-test and t-test both test means. The one-prop z-test tests the proportions. Okay, in the z-test, the standard deviation is known, and in the t-test, the population standard deviation is unknown. Okay, so I got to go back up, just double check and see if they told me anything about a population standard deviation. They gave me a population mean, but no population standard deviation is found in this problem. So that tells me I'm going to be running t-test. I'm interested in a mean, standard deviation is unknown. All right, so now I'm going to go to my calculator. I'm going to go over to the t-test here. Clear that off my screen, go stat. They didn't give me any raw data for this one. They just told me what happened with their sample. So they told me we took a sample of 41, and then they told me what the sample mean and the sample standard deviation was. So I don't have the raw data. So this time when I go to my t-test, I'm going to select the stats option because they didn't give me the actual data, but they gave me the results, so I can use that. And we're assuming that the mean is 120 here. That's what it's supposed to be. And the sample mean that we got, my paper over here, there we go. So the sample mean that we got was 118.8 with a standard deviation of 5.2 grams. So this is a sample standard deviation, and our sample size was 41, and we are running, oops, typo. That t-test. We are running a left tail test here, so everything's still entered. That's good. The left tail test, and we'll go to calculate. See what we get. All right, so there's our test statistic, right? Our test stat, negative 1.477. So this tells us we're 1.477 standard deviations to the left of what we expected to get. The p-value of that, so the probability of that happening, is about 7.3, 7.4%. Okay, so I'm going to write those numbers down here. So I'm going to say that my test stat t equals negative 1.48 if you round to 2 decimal places, and my p-value equals 0.074. And now I got to use that to make a decision about the weight loss. Okay, so I'm going to take my p-value, 0.074. I'm comparing it to my significance level, which is 5%, and the 0.074 is greater than. Okay, so while 7% chance of something happening is pretty low, it's not low enough to convince me that the drug causes weight loss. Okay, so it just wasn't rare enough. This is not a small enough probability for me to reject the null hypothesis. So I'm going to fail to reject the null hypothesis. And then I'm going to go write my conclusion in context. What does that mean in English? Okay, so get that typed up for you. All right, and there it is. There is not, right? So notice the difference in the wording here. There is not sufficient evidence to support the claim that the new drug has changed the mean mass of the rats to be less than 120 grams. There are different ways to word that. So this is not the only way that you can word that. This is just how I would have worded it. So, you know, that's why when you get to the quiz, when you get to the homework and stuff like that, there's just going to be a free response thing where you type in your conclusion in context, and I will grade it. But do be careful with your wording. Make sure that it says what it's, you know, make sure that it's logically sound and that it makes sense. And pay attention to the feedback that I give you in the homework when you write these statements to help you correct them. If you've said something wrong, I have to correct it. All right. So that's it for this video. Again, if you have any questions about anything, make sure you email me and we can get those ironed out. All right. Have a great day, guys.